Hello everyone. In the previous lecture we have seen or we have solved exercise 5.1, and now today we are going to see section formulae. Means section formulae in the form of vector. Actually everybody studied up to 10th standard section formula. So I will just revise the concept which we have studied in 10th standard. So see, section formula first here. See, if we have a segment AB, and if this segment AB is divided internally at the point R in the ratio m/n, then by the section formula we have, if that point R has coordinates x, y, point A has coordinate x1, y1, and point B has coordinates x2, y2, then by section formula we have small x is equal to mx2 plus nx1 divided by m plus n. And this is the formula for x coordinate of the point R. Similarly for y coordinate, my2 plus ny1 divided by m plus n. Or if that point R divides externally, means if that point is like this, point A, here if it is B, or here it is B, and point R is here, then this point R divides the segment AB externally in the ratio m/n. In this case, and if point R has coordinates xy, B has coordinates x2, y2, point A has coordinates x1, y1, in this case small x is equal to mx2 minus nx1 divided by m minus n. And for y coordinate it is my2 minus ny1 divided by m minus n. Or if the point R divides, in this case internally in the ratio 1:1, it means that if point R is midpoint, then your x is equal to x1 plus x2 upon 2 and y is equal to y1 plus y2 upon 2. If that point R divides the segment AB internally in the ratio 1:1. So this is everything which we have studied in 10th standard. Today we are going to see the section formula for vectors. So let's see some theorems. Yes, theorem. Statement of the theorem. Let point A with position vector A bar, comma, point B with position vector B bar be any 2 points and be any 2 points in this space. Be any 2 points in the space and the point capital R with position vector R bar, small r bar, be a point on line segment AB, be a point on line segment AB dividing it internally in the ratio dividing it internally in the ratio m/n, then R bar is equal to m into b bar plus n into a bar divided by m plus n. Okay, now this is the statement of the theorem. Now let's see the proof. See, let A with A bar and B with B bar be any 2 points in this space. Suppose, see, these 2 points are here, A, and this is point B. And this is segment AB. The point R with R bar divide segments AB internally. So point R with position vector R bar is here. This is the point A with position vector A bar, and this is the point B with position vector B bar. So this is point O, so this is OA bar, so it is A bar. It is OB bar, this is B bar, and this vector is R bar. See, let A with A bar and point B with B bar be any 2 points in this space. The point capital R with R bar divides segment AB internally in the ratio m/n. So point R with R bar means this distance is m, means length of AR is m and length of RB is n, in the ratio m/n. AR, see, AR and RB, AR and RB have same direction. AR and RB have same direction, means vector AR and vector RB have same direction. See here from this figure, AR, baga, direction is south to north. RB, direction is from south to north. So both vectors have same direction, as well as point R divides the segment AB internally in the ratio m/n. So therefore AR as to RB is m/n. So therefore AR upon RB is equal to m divided by n. So therefore n into AR is equal to m into RB. See, the vectors n into AR bar and m into RB bar have same direction and magnitude. M into RB and n into AR bar have same magnitude as well as same direction. So therefore, how same magnitude? Directions are same. AR bar south to north. Sorry, north to south, and here RB, it is also north to south. Both have same direction. What about magnitude? See, n into AR bar. N is scalar, n into magnitude of AR bar, that is the length of segment AR, and that is m. So its magnitude become n into m. Here m into RB, what is the magnitude of RB? That is the length of segment RB, and that is n. So m into n. So the magnitude of this vector is mn, magnitude of this vector is also mn. So therefore both vectors have same magnitude and same direction, so therefore they are equal. So therefore n into AR bar is equal to m into RB bar. Now by using the definition of position vector, n into AR bar, see, in the form of position vector, AR bar is nothing but the position vector of the point R, that is R bar, minus position vector of the point A, that is A bar. It is equal to m into RB bar, this is position vector of the point B, that is B bar, minus position vector of the point R, that is R bar. So therefore n into R bar minus A bar is equal to m into B bar minus R bar. Now multiply to the first bracket by n, so we get n into vector R minus n into vector A is equal to m into vector B minus m into vector R. See, n into R bar, shift this minus n into A bar to right hand side and minus m into R bar to left hand side. So we get n into vector R plus m into vector R is equal to m into vector B minus become plus n into vector A. Take here n into R bar, m into R bar is common in both the terms, so we get m plus n into R bar is equal to m into vector B plus n into vector A. That is, R bar is equal to m into vector B plus n into vector A divided by m plus n, and that is what we want to show. This is the proof of this theorem. R bar is equal to m into B bar plus n into A bar divided by m plus n. If the point R with position vector R bar divides the segment AB internally in the ratio m as to n. Note. If your capital A is A1, A2, A3, capital B is B1, B2, B3, and capital R has coordinates R1, R2, R3. R1, R2, R3, Ri is equal to m into Bi plus n into Ai divided by m plus n. So if you want to find out R1, so R1 is equal to m into B1 plus n into A1 divided by m plus n. If you want to find out R2, so R2 is equal to m into B2 plus n into A2 divided by m plus n. If we want to find out R3, then R3 is equal to m into B3 plus n into A3 divided by m plus n. So in this way, the coordinates of point R can be found. Note number 2. If here point R divides the segment AB internally in the ratio 1:1, means if point R is midpoint, if R with R bar is midpoint of segment AB, then R bar is equal to A bar plus B bar divided by 2. If it is midpoint. So this theorem and these two notes are very important. Now we see next theorem. The first theorem is section formula for internal division, because the point R divides the segment AB internally in the ratio m as to n. Now here, if the point R divides the segment AB externally in the ratio m as to n, then what is the section formula? And that section formula is called as section formula for external division. So we see the theorem of section formula for external division. See, let point A with position vector A bar and point B with position vector B bar be any 2 points in this space and point R with position vector R bar divides segment AB externally in the ratio m as to n, then your R bar is equal to m into B bar minus n into A bar divided by m minus n. M into B bar minus n into A bar divided by m minus n. Okay, we see the proof of this theorem. See, we have 2 points in the space, A with A bar and B with B bar. Suppose these 2 points are here. A, and if this is B is here, A with A bar and this B, point B with B bar. So the position vector of point A is A bar, so OA bar is equal to A bar. The position vector of the point B is B bar, means it is B bar. This is segment AB, and this segment AB is divided externally, means your point R may be here like this, or your point R may be here. If it divides externally, it is either here or here. Suppose we consider the point R is here. And see, this position vector of the point R is small r bar. So right here, let A with A bar and B with B bar be any 2 points in this space. Space means here, the point is here. In this space, the point R with position vector R bar divides segment AB externally in the ratio m as to n. So therefore, either the point R is like this, A, B, R, or R, A, B. Means point may be here or point may be here. Let the position from the figure, the position of the point R is A, B and R. Now the point R divides the segment AB externally in the ratio m as to n. So here the point R with position vector R bar divides the segment AB externally in the ratio m as to n. It means that this distance is m and this distance is n. Means the length of AR is m and length of BR is n. So therefore, AR, the ratio of AR as to BR is equal to m as to n. The ratio of AR with BR is m as to n. See here, AR and BR. See, AR direction is from north to south. BR, the direction is from north to south. So AR and BR both have same direction. AR and BR have same direction. So therefore, AR divided by BR is equal to m divided by n. So it is n into AR is equal to m into BR. That means n into AR, or we have to mention the reason here, since n into AR bar and m into BR bar have same magnitude and direction. Magnitude and direction. Baga, how from figure the direction is same. AR this direction and BR this direction. Both have same direction. What about magnitude? N into AR bar. Magnitude of AR bar is nothing but the length of the segment AR, and that is m. N into m become mn. What about the magnitude of m into BR bar? M into magnitude of BR bar is n, because that is the length of segment BR. So this is m into n and this is n into m. So both have magnitude mn. So mn is equal to mn. Since n into AR bar and m into BR bar have same magnitude and same direction, and we know that by the definition of equal vectors, n into AR bar is equal to m into BR bar. So now use the definition of position vector and simplify this. That is n into position vector of R bar, that is R bar minus A bar. AR bar, see, AR bar is nothing but position vector of the point R, that is R bar, minus position vector of the point A, that is A bar, is equal to m into position vector of the point R, that is R bar, minus position vector of the point B, that is minus B bar. So here n into R bar minus A bar. So multiply to this bracket by n. So n into R bar minus n into A bar is equal to m into R bar minus m into B bar. Now see here, shift this m into R bar to left hand side and minus n into A bar to right hand side. So we get, or shift this minus m into B bar here and minus n into bar there. So we get, it is m into B bar minus n into A bar is equal to, here we have to shift this n into R bar to right hand side. So it is m into R bar minus n into R bar. Now m into B bar minus n into A bar is equal to, see here, m into R bar minus n into R bar. R bar is common here. So it is m minus n into vector R. So therefore m into B bar minus n into A bar divided by, shift this m minus n to left hand side. It is at numerator. If we shift it to left hand side, it goes to denominator. So it is m minus n is equal to R bar. So therefore R bar is equal to m into B bar minus n into A bar divided by m minus n. And this is the section formula for external division. The difference between section formula for external division and internal division is only the sign. In external division it is minus and in internal division it is plus. So these are the two theorems of section formula for external division and section formula for internal division. Okay, now we see note or remarks of this theorem. In some problems, it is asked that find out the ratio in which the given point divides the segment. At that time, it is convenient to take, means in that problem we have to find out m as to n, and so to get m as to n, it is convenient to take the ratio as k as to 1. So this is first remark, first note. Whenever the ratio in which point r divides, whenever it is asked to get the ratio in which the point r divides segment AB, it is convenient to take the ratio as k as to 1. K as to 1. It means if we have to find out the ratio, at that time take the ratio as k as to 1 and get the value of k, automatically we get the ratio in which the point r divides the segment AB. So if we take the ratio as k as to 1, so in this case your r bar become k into b bar plus 1 into a bar divided by k plus 1 if the point r divides segment AB internally. If it divides externally, so we get r bar is equal to k into b bar minus 1 into a bar divided by k minus 1. So this is first note. Now second note, if this capital G is the centroid of triangle, ABC, centroid of triangle ABC. So see here, if this is the triangle, point A with position vector A bar, point B with position vector B bar, and point C with position vector C bar. You know that this is and this is centroid G, and the centroid G is the point of concurrence of medians of this triangle. And you know that the point G, so if this is point D, then the point G divides the segment AD internally in the ratio 2 as to 1. And in this case, the position vector of the point G is suppose small z bar, then small z bar is equal to a bar plus b bar plus c bar divided by 3. And so this is centroid formula. This is called as centroid formula. Now note number 3. If we have a tetrahedron, if capital G with small z bar is the centroid of tetrahedron, A, B, C, D, then small z bar is equal to a bar plus b bar plus c bar plus d bar divided by 4, where the small a bar, b bar, c bar and d bar are the position vectors of the vertices A, B, C, D respectively. So here, if we want to find out the ratio, take the ratio as k as to 1. It is convenient, it is easier one to get the ratio as m as to n. In second note, if G is the centroid of any triangle, then the position vector of that centroid of the triangle is given by z bar is equal to a bar plus b bar plus c bar divided by 3. And if the centroid of tetrahedron is given, then the position vector of that centroid of tetrahedron is a bar plus b bar plus c bar plus d bar divided by 4, where the a bar, b bar, c bar, d bar are position vectors of the vertices a, b, c, d respectively of tetrahedron. So today here we have discussed section formula for internal division and section formula for external division and their remarks. In the next lecture we will solve examples on the basis of centroid formula. Thank you.